All right, in the previous class, we have gained an insight into the operation of ionic gas lasers, and we now know that the active medium in that ionic gas lasers is ions, that is the light emitting species or ion, which are actually manufactured in the gaseous discharge uh, by stripping electrons from the outermost electrons from the neutral atom. And these ions are actually capable of emitting light at a much shorter wavelength, lying in the ultraviolet or in the lower wavelength side of the visible spectra. The lasers are pumped in the electric discharge by collisions with inelastic collisions with electron, just like the operation of atomic gas lasers, but only difference with atomic gas lasers is that the active species, that is the ions, are also created in the discharge by colliding, by collisions with electrons. That is why these lasers operate at a much lower operating efficiency compared to the atomic gas lasers. We also have studied the working on one of the most popular and important ion laser, that is argon ion. We have seen that when pumped, population inversion in case of argon ion laser occurs at a number of wavelengths. And we also have studied the emission characteristic of an argon ion laser by operating the laser both in non-dispersive and dispersive cavity mode. Let us refresh our memory on the operation of argon ion laser both in dispersive and non-dispersive cavity configurations. Let us first consider the case of a non-dispersive cavity. That is, inside the cavity there is no wavelength selective component. Now, when the medium is pumped and population inversion has set in on a number of transitions, then first spontaneous emission occurs on all these wavelengths. So let us assume there are 3 wavelengths in which population inversion now exists. There are 3 wavelengths. So spontaneous emission will occur on all these 3 wavelengths, and spontaneously emitted photons on all these wavelengths and spontaneously emitted photons from all these wavelengths, when they travel along the axis of this cavity, they work as the seed photons for the stimulated emission to take place. Then stimulated emission begins and amplification of light occurs from all these 3. And as there is no wavelength selective discriminating element inside the cavity, therefore all these 3 wavelengths will simultaneously grow and basically extract energy from the gain medium, which is continuously being pumped towards maintaining population inversion to allow the laser lays in a continuous manner. Now this light that builds up all these 3 wavelengths, part of the light actually is coupled out of the cavity, which forms the laser beam, and it contains all the 3 wavelengths. And if you shine this output beam of the laser onto a prism, then the prism will split the 3 wavelength components spatially, as you can see here. Thus, the non-dispersive cavity laser will emit multiple wavelengths. Now let us consider the case of dispersive cavity. Here again, after pumping, population inversion will exist on all those three transitions, that is lambda 1, lambda 2, and lambda 3. And spontaneous emission begins on all these. And initially, there will be some stimulated emission, single pass stimulated emission, so there will be some amplification of light as it travels through the cavity, travels through the gain medium, and this light of pure wavelengths shines onto the prism. No, now it is a dispersive cavity, so now the prism, which is a very simple dispersive element, is placed inside the cavity. So these three wavelengths, light at these three wavelengths shines onto this cavity, onto this prism. The prism then splits these wavelengths spatially, allowing at a time only one of the wavelengths to fall on the output mirror obliquely. You can see only this wavelength falls on the output mirror obliquely. And therefore, this wavelength alone will be able to oscillate back and forth inside the cavity, back and forth inside the cavity, and it will grow. The other wavelength, which fall on the output mirror obliquely, like this lambda 2, or lambda 3 here, you can see it misses the output mirror altogether. Therefore, they would not get any chance to laze at all. So, the light inside the cavity can grow only on this wavelength, lambda 1, which can oscillate back and forth, because this is the wavelength which only shines onto this output mirror normally. So then the laser will emit wavelength lambda 1. Now, if you have to tune it to the wavelength lambda 2, then you have to just tilt this mirror, say this way. And basically, now the position of the mirror will be somewhat like this. So that now this wavelength falls normally onto this mirror. And this will be reflected back and we'll be able to oscillate back and forth inside the cavity. And this wavelength now falls obliquely on this mirror and would simply get lost. And the same would be true for the other wavelength also. So now the cavity, the laser will laze on wavelength lambda 2. Similarly, by tilting it further, you can now bring this wavelength lambda 3 into lasing, while both lambda 1 and lambda 2 now would get lost. Now the same effect also can be obtained by tuning appropriately, by tilting appropriately the prism to ensure that at a time only one of the wavelength falls on the output mirror normally. You tilt this prism and you will get the same effect. So this way you can actually tune your either output mirror or the dispersive element and make the laser emit on different wavelengths on which you have established gain as the result of pumping the medium. Thus, a dispersive cavity laser will operate on a single line. So that thus, this results in single wavelength laser. So in a dispersive cavity, you will get single wavelength. Now let us explore what would be the monochromaticity of this argon ion laser and how does it compare with the monochromaticity of an atomic gas laser, say for instance the helium neon. So for this, let us go a little deeper. You see, in this case, you will have to extract more energy, more power from the line for the operation of these lasers. That is because you will have to create the light emitting species, which in this case are argon ions. So, how do you do that? You couple, of course, the energy that you have drawn, you couple it into the discharge. How? As the kinetic energy of the electron. So the energy that you draw from the line is actually translated first as the kinetic energy of the electron. The energy stays locked up. So you have drawn energy from the power from the line, and this is your electric discharge. I'm giving you a very qualitative picture. So you have drawn more power from the line, and this extra additional energy which you have drawn is also being realized in the beginning as kinetic energy of the electron, basically. Now these electrons then collide with argon, neutral argon atom, and if the electron's energy is large enough, it will ionize argon atom, and argon ion will be created, which will work as the light emitting species for, and you will create an additional electron, and this electron will move with lower current. Now, the additional energy or power that you have drawn is not that the entire power or energy is being consumed in the production of argon ion, because as you know, the energy, the electrons in the discharge, the kinetic energy of the electron, essentially the velocity of the electron, will follow a Maxwellian distribution. That means the electrons will have a range of velocities. This is the velocity, and this is number of electrons with that velocity. So for this process, this is manufacturing argon ion, not all electrons will be equally effective. The electrons that will have an energy more than the ionization potential will only be able to ionize argon atom. So that may be just a part, a fraction of this electron which will participate in this process. And then the second process, once argon ion has been formed, then it will again collide with electron which has the adequate kinetic energy. It will actually excite the argon ion to the excitation, that is the pumping. You are creating population inversion. That also take advantage of the electron, of the kinetic energy that is locked up in the electron through such inelastic collisions. But not all the energy that you have drawn from the line is consumed in the production of argon ion and the creation of population inversion. A large fraction of energy stays locked up as kinetic energy of the electron and remains unutilized. This eventually is dissipated as heat and increases the temperature of the gas. Now, so coming back to the original, what will be the monochromaticity of this? So now if you consider the case of helium-neon laser, where, of course, the energy is also again dissipated and heats up the gas, but because less energy is dissipated in the lasing volume, the temperature rise for helium-neon laser will be less than for argon, because you have to draw more power, simply because you will have to create enough number of light emitting species. That is, we have to strip lot many neutral argon atoms, strip off their electron and manufacture argon, that light emitting species. So then there will be more dissipation of energy into the discharge that will increase the temperature of the gas, discharge temperature. So for helium-neon laser, if the velocity distribution of electrons is like this, so this is at a temperature T1, this is for helium-neon. Then for argon ion, this is going to be like this. This is at a temperature T2, where T2 is more than T1. Actually, it is much, much more than T1. So that means the velocity has a much wider distribution. All right. So sorry, I must say that this is the gas, this is the temperature of the gas. So this is the velocity distribution of the neon atoms, which are light emitting. This is for helium-neon laser. And this is the velocity distribution of argon ion. So the velocity range of velocity of argon ion is much wider because the temperature is more in this case. And that says that the Doppler broadening for argon ion laser is much more compared to the helium-neon laser, because the velocity spread is less here. Velocity spread here is less compared to the case of argon. And more is the velocity spread, more would be the Doppler broadening. I have already explained Doppler broadening in the context of helium-neon laser. As a matter of fact, the Doppler broadening for helium-neon, typical helium-neon laser, that is gain broadening due to Doppler effect, for a helium-neon laser is 1.5 gigahertz. So this is usually defined as the full width at half maximum. So this is 1.5 gigahertz. Or 1500 megahertz. And this is frequency. And for argon ion laser, because the velocity range is much wider here, the broadening, Doppler broadening is also much larger. This is about 5 gigahertz in the typical operating condition. That means 500 megahertz. Which is more than 3 times the broadening, Doppler broadening for helium-neon. So this is helium-neon. So in this, if we plot the gain of argon ion. So this is the gain. This is for helium neon laser. Now let us plot the gain of argon ion laser, normalized gain. So it would look somewhat like this, very qualitative. Somewhat like this. So the broadening now is 500 megahertz. Let us assume that the cavity length for both this laser is say about 50 centimeter. It is the length of the cavity for both the lasers. 50 centimeter. This is helium neon and this is argon. So 50 centimeter cavity length, the free spectral range, which is equal to C by 2L, where length L is the length of the cavity. In this case, it is velocity of light is 3 into 10 to the power 8 meter per second divided by 2 into L. L is 50 centimeter, so half meter. So this is equal to 300 into 10 to the power 6 hertz. So this is equal to 300 megahertz. So free spectral range is the spacing between two adjacent cavity modes. Now, so cavity modes, there will be innumerable number of cavity modes spread all around the spectrum. So let us draw some cavity modes which overlaps with the gain. So these are the cavity modes which will extend on either side of this gain. There will be innumerable, ranging from -0 to infinity. So now, so these are the gains, and this is frequency. Now we ask the question, how many modes will lays for the operation of helium neon laser, and how many modes will lays the operation of argon? So for this, we must first know the location of the loss line. Suppose for both the lasers, just for sake of clarity, for simplifying this explanation, we assume that for both the lasers, the loss line is located somewhere here. So this is the loss line. Loss line. And loss line is parallel to the frequency axis. So we assume that it doesn't depend on the cavity loss, doesn't depend on the frequency. So what will be the, how many modes can lace? So for example, if you consider the case of helium neon, this is the lasing window. The lasing window is basically the intercept of the loss line with the gain curve. Because you see, outside this, if you go outside this, for example, this cavity mode, this lies outside the lasing window. So its gain is this much and loss is more. So this cannot lace. Or if you see this mode, which lies just outside the lasing window, its gain is this much and loss is this much. So this cannot lace. So only those modes which lie within the lasing window will be able to lace. So you see, in case of helium neon laser, there are 1, 2, 3, 4, 5, 6, 7 modes which lie within the lasing window. So they all will lace. So this will be helium neon laser, will be multi-mode laser, and 7 modes will manage to lace. However, what happens for argon ion laser? So this is again the lost line. So for argon ion laser, this is the lasing window from here to here. And how many modes lie within the lasing window? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, almost 18 modes. So both are multi-mode laser. Both lasers operate under this loss condition as multi-mode lasers. But for helium neon laser, number of modes that can come into lasing is much less compared to argon ion laser. If less number of modes come into lasing, then the emission width of the laser will be narrower than when more number of modes come. So in the multi-mode operating condition, the monochromaticity of helium neon laser is going to be much better than that of argon ion laser. Both are operating in multi-mode. Now let us see if we can force single mode emission by appropriately locating the loss line. What we do in order to reduce, so you have to basically reduce the lasing window. How do you do that? You increase the loss. If you increase the loss, so the loss line will go up. Suppose you bring the loss line here. So you can see here for this much lasing window, if you look at the modes for helium neon laser, now 1 and 2, these 2 modes will only have gain exceeding loss. The other modes will be out of lasing because for them the loss becomes more than gain. This is now the loss line. This is now the loss line. So now lasing will be on 2 modes. If you push it further up, say we take the loss line here, you can now see that now the lasing window becomes less than the free spectral range. Under this condition, only one mode, that is this mode, will have gain exceeding loss. So it will be a single mode laser, and then it will be highly monochromatic. Its emission width also will be very, very small. Now, let us consider the case of argon ion. Can you force argon ion laser into single mode, force emission of argon ion laser on single mode? You see, basically, the top of the gain curve of argon ion laser is so flat that 2 or 3 neighboring modes you can see have almost similar gain. That is because it is so much flattened, because the broadening is so much more, the top becomes very flat. So few neighboring modes have almost similar gain. So by increasing the loss, it would be very difficult, very challenging to force emission of argon ion laser on a single mode. Thus, we come to the conclusion that Argon ion laser would actually encompass many longitudinal modes. For a laser of typical cavity length, it will be, of course, a multi-mode laser with very large emission weight. And a dispersive cavity laser, although will operate on a single line, but on multiple longitudinal modes. But on multiple longitudinal, it would be very challenging to force the emission of argon ion laser single mode. I think I will stop here today. So that ends the course on operation of ionic gas lasers.